Okay, picking up from question 10, I've got two balls and I've got a tall building. So they're going to come off like this and they're both going to undergo a parabolic path. So what I know about, I've got ball P, I've got ball Q. I know that their surface area is the same because it's the same diameter, I know their volume's the same, but I know that the mass of P is bigger than the mass of Q, which means that the weight of P is also bigger than the weight of Q, because weight and mass are proportional to each other. So let's think about our two directions. Vertically, they've got the same downwards acceleration, so they've got downwards 9.81. And then the upwards, so P's got a larger force downwards. So P's got a larger force. They've got the same diameter, so the air resistance initially is the same. And there's two things here that's going to make P reach the bottom first. So number one, if we think about this force diagram, we've got the weight there and we've got the drag there. So the weight of P is bigger so that means that the net force, the one pulling this one down, is going to be bigger. So our acceleration is going to be higher downwards. Also, with a higher weight, the terminal velocity will be higher. So that means the time taken to fall, both accelerating and having a higher terminal velocity, so the time it takes for P to fall is going to be less than the time it takes for Q to fall. So that gives us either this one or this one, C or D. And then thinking horizontally, so both balls have a horizontal velocity u, that's the same for both. Both balls have the same drag, so this is the same, this is the same, because they've got the same dimensions, and we're not reaching terminal velocity. There's no forwards force, there's no force speeding them up, so the only force is slowing them down. If we've got the same force and F equals ma, then one's going to slow down more than the other, and if I've got A equals F over m, then the more massive one slows down least. So the one that slows down least is the one that's going to go the furthest. So the more massive one, which is P, slows down least, so P slows least horizontally. So let's say that the acceleration is less, so the acceleration of P is less than the acceleration of Q. I wonder if we've got an equation that can link those two things. So if v squared is u squared plus 2as, is that going to help us? Yeah, I think so. Or maybe s equals ut. No, that's got two variables in it. We'll stick with the other one. So v squared equals u squared plus 2as. So u squared isn't changing. So I could say then I want to get a and s on the other sides of the equation. So I could say s equals v squared minus u squared all over 2a. So the s is inversely proportional to a. thinking about if the final velocity is the same, which isn't necessarily, but the bigger the acceleration, the smaller the distance. So dq is going to be smaller. It's going to be that one. Okay, let's have a look at number 11. A firework moves vertically upwards, burns at steady rate, produces a constant thrust, and the mass of the rocket decreases with time, ignoring air resistance this time. Which row shows the acceleration of the rocket before and the acceleration immediately after the fuel has been used up? So immediately after the fuel has been used up, it's going to have to be constant downwards because then there's no upwards force. If I think of my rocket, if it's got a constant force but a mass which is decreasing, if F equals ma, and F is constant, mass is going down, A has to go up. So acceleration happens in the direction of the force, so we're going to have an increasing upwards acceleration there. So question 12. Object P has a mass of 7. Let's have a P. Oh, we've got a P and a Q again. And they're going in the same direction. Which one's going faster? Let's have Q over here. So that one's going 20 meters per second. They're going in the same direction. That's 12 meters per second. And then we got 2,500 kilos and 7,500 kilos. And then they collide, so that's my before, and then my after, that's P plus Q. We're definitely going in the same direction. We know the combined mass is going to be 10 tons or 10,000 kilograms. I don't yet know what the velocity is going to be. But what I can do is I can say, so we know they join together, so it's inelastic. So that means momentum's conserved, but kinetic energy conservation, that's a no-no. So I'm going to have to figure out the velocity first. I can't figure out the kinetic energy at the start and then call out the same because they join together, so they can't be an elastic collision. So I'm going to do 20 times 2,500 plus 12 times 7,500. I don't need any brackets there because of bid mass. And then I'm going to have 10,000 times V. So I'm going to put this into my calculator. I go 20 times 2,500 plus 12 times 7,500. The way I do this is I press equals and I divide that by 10,000, giving me V is 14. So after the collision, I know my kinetic energy is a half mv squared. So that's a half times by 10,000 times by 14 squared. This is going to be big. So I'm going to square the 14 times by 10,000 times by 0.5 on my calculator to keep it all on one row. That's 980,000. So that's 980 kilojoules. Shave that one in. So then 13, I've got a climber wearing a harness, the rope passes through a brake, there's friction between the rope and the brake. The climber uses the brake to descend at a steady speed of that. The combined mass of the climber, the harness and the brake is 60 kilograms. So this is telling me if we're descending at a steady speed, that the upwards force, if if I'm descending at a steady speed, then the force due to the brake equals the force due to the gravity, or let's say force due to gravity, that's the weight. Excuse me. So, in order to find the power, so rate of energy transfer, that's power. I know that power is force times velocity. So in this case, I know that the force is equal to the weight, which is 60 times 9.81, and my velocity is 0.5. So I go 60 times 9.81 times 0.5, and that gives me 294.3, which is D, which isn't too bad. Question 14 says a solar panel powers a pump for a water feature. Solar energy is incident on the panel at a rate of 1.5 watts. Water from the bottom of the container is continually pumped through a vertical height of 0.6 meters. So I've got the energy to get to the top, that's mg delta H. And all of that energy is coming from my solar power, which is 1.5. That's how much energy per second. So that's joules per second. So if I say mass per second, that will be fine. It says the overall efficiency of solar panel pump is 20%. So I have to times that by 0.2. I know the height, right? So then if I can get rid of the S, or at least what I'm trying to find is M over S, so the mass per second. So that's going to be 1.5 times 0.2 divided by 9.81, which is G, times by the change in height, which is 0.6. So if I do 1.5 times 0.2 divided by 9.81 times 0.6, I have to use some brackets here but in my calculator just because I do worry. That gives me 0.0509.6, etc. So that's 0.05 kilograms, and in grams that is 50 grams. Okay, this time I've got looks like a moment's question to me. A uniform meter ruler of weight 2 newtons is freely pivoted at the 70 centimeter mark. What's the magnitude of the resultant moment when the student releases the ruler? Okay, so I've got a turning effect, which is going to be 5.0 times 0.3. And then I've got a turning effect from the weight of the ruler. If I take that away, so that's going to be 2 newtons times, because those are going in opposite rotational directions, I'm going to take one away from the other. I might get a positive or a negative answer, I don't know yet, but it doesn't matter because I'm looking for the magnitude. All I know is I have to take one away from the other. I can make either rotational direction positive. And I know that since that's a uniform meter ruler, that point is 20 centimeters from the center of mass. I've got 2 times 0.2 on that side. So I do that on my calculator. I get 5 times 0.3 minus 2 times 0.2, giving me 1.1 Newton meters. That's the difference between those two. I don't know, it's positive, so it looks like it's going to be in the clockwise direction, but it doesn't ask me about that direction, only about the magnitude. So for question 16, I'm looking on a solid square object seen from above. All the forces have the same magnitude. which system produces a couple about any point inside the object. So let's just pick the middle because that's easy. Those two aren't going to be opposite. Those two aren't going to be opposite because if I talk about that distance there and that distance there, they're not producing forces aren't equal and opposite, and in fact that one there, they're not opposite either. Oh, I've lost my pen. Oh, in fact I've lost everything. In fact the whole laptop has crashed. Okay, we're back. Let me just double check that we're still recording a second. Yeah, we're good. Okie doke. So the one that's equal and opposite is going to be D on that one. The forces have to be equal and opposite. Not just the moment, the forces. So an electron has speed v. The electron's kinetic energy is doubled. What is the new speed of the electron? So I know that kinetic energy is a half times mass times velocity squared, which tells me that the kinetic energy is proportional to, so for the same thing, which is an electron, half is a constant, mass is a constant, the kinetic energy is proportional to v squared. So if I double the kinetic energy, I have to do the same thing to the other side. So I double v squared. But in order to double v squared, the question is, what do I have to do to v? So I have to try and get that 2 closer to the v. So if I do root 2 times v, and then you can see if I square this again, root 2 squared is 2 and v squared is v squared. So that gets me to the same point. So that's what happens to v in order to double v squared. So that one is B. 18. An object of mass m is accelerated from rest to a velocity v by a constant resultant force F. What is the work done on the object during this acceleration? So if work done is force times distance, in fact, we can make this slightly easier. So if I go from kinetic energy equals 0 to kinetic energy equals a half mv squared, then the work done to get from 0 to there equals a half mv squared. So it's got to be D. So if my acceleration is constant, what else could I do? How else can I get there? So if work done is force times distance, I don't know, kind of stick with that one, it's pretty straightforward. Start with a velocity and end with a different velocity. I could even do that if I didn't start. It does say from rest actually. So I go from 0 kinetic energy to some kinetic energy, so the kinetic energy must be the work done. Excuse me, I have a bit of a cold. What is true for an inelastic collision between two isolated objects? So momentum conserved, yes. Kinetic energy conserved, no. So it's gonna be both total moment, so that's a no for that one. It has to be, that's not true because always momentum is conserved. Kinetic energy is not conserved because it's inelastic, so it has to be D for 19. Looking at 20. This is a tricky one. So I know if this, so they're joined by a rod, there's no mass of the rod, and you've got masses there, the distance between those that which diagram shows the position of the centre of mass? So if I think about the centre of mass, the moment from P and the moment from R must be equal. So if I know that mg, let's call, or what shall I do? I should really use the letters that are on here. So if I go mass of P times G times distance, which we're going to call L. In fact, this is probably easier if I start at one end, isn't it? Or is it? Or can I not do that? So the moment from P equals the moment from R. I feel like there's an easier way to do this. I'm pretty sure there is. Let's take moments about P. So if I say that the mass of R times G struggling. Let's take a pause there.